This is lab 5 for physics 2212, the Faraday's Law lab. The purpose of this lab was to collect the data of a magnet falling through a conductive tube and observe how long it takes. We wanted to apply the concepts of flux, Faraday's law, and Lenz's law, and create a computational model and compare with the observational data. Here's the models and fundamental physics principles used in this lab. First one is the Biot-Savart law, which is shown there. And then Faraday's law, which is shown below it, and then Lenz's law, which is the fact that a magnetic field generated from an induced current flowing in a loop is the opposite direction of the change in flux through the loop. And then the magnetic force on a wire is equal to I delta L XB. And the magnetic flux is the measurement of the total magnitude field passing through a given area. The results in this lab, the experimental time was 1.51 seconds, and the computational time was 1.65 seconds. Here's the procedure. First, we created a tube out of foil and took the dimensional measurements, and then determined which end of the magnet was north, and then dropped the magnet through the loop and recorded a video of the magnet entering and exiting the tube. In the video from the time codes in it, I just used when the magnet entered the tube and exited to find the time it took. And then I repeated this 5 times to find the average time. Here's the data from the 5 trials. I had 1.38 seconds, 1.61 seconds, 1.52 seconds, 1.63 seconds, and 1.42 seconds for an average of 1.5 seconds. The other data is shown on the left, which is the length of the tube was 0.3 meters. The width of the tube was 0.006 meters. The inner radius was 0.02. The mass of the magnet was 0.021 kilograms, and the magnetic dipole moment was 3.4. Observations are that the magnet falls slower than it would have in free space, and the downward force of the magnet has less magnitude because the cylinder foil applies an upward force on the falling magnet. The lab uses the following assumptions: that the system only contains the aluminum foil and bar magnet. Obviously, there's other forces like air resistance that are involved that aren't included here. So for the simulation, this is the code that creates the graph and gets the measurements. And then this is the code that creates the tube and the bar magnet. And then this is the code that calculates the derivative of flux, the analytic solution here. So that function is shown below. And then this is creating the simulation. The code results are shown here, which is the velocity versus time, and it takes 1.653 seconds in the simulation. So the red and blue in the tube are currents flowing in opposite directions, and in my experiment, the north end was pointed towards down because it's falling. And because the magnetic field points out of the north end and the magnet was getting closer to the loop, there was greater magnetic flux in the downward direction of the loop, and induced B fields point in the opposite direction of change of magnetic flux. So there's some sources of error here. Most of the labs, since it was using technology, had little human error, but it could have been measurement errors when measuring the foil and finding the times, because like iPhone cameras can't record everything super accurately. For the what if questions, if the resistivity of the conductor was reduced as close as possible to 0, the dynamics of the falling magnet would change because the induced current would increase and approach infinity due to Ohm's law. And due to the increase in current, the magnet would take longer to fall through the tube because F is equal to ILB. So if current increases, then the magnetic force on the loop will also increase. And if there were holes or slots cut into the tube, this would affect the ring currents in the model. There'd be less rings in the model because there's less loop area, meaning lower magnetic flux. And the induced current and magnetic force would be smaller, meaning that the time for the magnet to fall would decrease. F is equal to, again, the same equation.